Next, we will move on to the hazards in your sequential circuits. So consider especially in an asynchronous sequential circuits. So in the previous video, we discussed about how the hazards are occurring, is it? So in that case, if you see, there is a static 1 hazard, static 0 hazard, and dynamic hazard. That is one more hazard is there, that is your essential hazard. The essential hazard is also that we discussed in the previous class, that is what it exists in an asynchronous sequential circuits. You know, the sequential circuits, there exists a feedback, and here we are going to consider that essential hazards and how it can be overcome. Okay, so let us consider an asynchronous example. See here, the asynchronous in the sense, so it's a sequential circuits, is it? And it's especially an asynchronous in which there is no such clock is utilized. See, the output here is connected as an input to this second AND gate, and for the first AND gate, x1 and x2 are given as an input. See, x1 dot x2 is your input to your first AND gate, and for the second AND gate it is x2 bar, and then the output of this circuit is given as an input, and hence it is considered as small y. It is x2 bar dot y. So this is the output for your second AND gate. This is given as an input to the OR gate, and you are getting a y is equal to x1 x2 plus x2 bar y. Okay, so now we are going to fill it in your K map. See here, you know that it is x1 x2, is it? It is x1 x2 in the sense this is your case, both are 1, hence 1 and 1 should be filled in the concerned cell. Okay, and then x2 bar y. Okay, x2 bar y. See here, this is x2 bar, and then y is this case. x2 bar is these two cases, is it? And then y is considered as these two cases, hence these two cells are filled with 1. Okay, so now if you combine this, see here that these two ones are combined and these two ones are combined, and there is a possibility to combine ones from different groups, which we can say it as a redundant groups. Here there, okay, see here you can combine these two ones, which meant that there exists a hazard during this switching. During this switching, in which when your x2 switches from 1 to 0, there exists an hazard. When x2 switches from 1 to 0, there exists an hazard. Hence, this should be overcome by adding. See, when it switches from 1 to 0, there exists a hazard. Hence, we need to group these two ones to form a redundant group. Okay, and hence, this is a simple by adding it to your a simple gate in which that is added to your asynchronous circuit. This is one way. The another way is we can use SR latch, in which a momentary 0 signal at SR inputs for NOR latch has no effect, and momentary 1 signal at SR inputs of NAND latch has no effect. Is it? Hence, there is a momentary change. During that momentary change, see here, this hazard is removed by adding latches to your output. Okay, see here, the hazard exists when you are moving from your x2 from 1 to 0. This can be avoided by adding NOR gates at your output, SR latch. You are using SR latch, in which a single SR latch can be considered, in which is using a NOR gate in which the output is connected as an input. The feedback case is considered. Okay, so let us see that if you add the NOR latch at your output, your hazards can be eliminated, in which you know the momentary change of 0 has no effects in SR latch of NOR, is it? So that is why a NOR gate is added here at your output to eliminate your momentary change of 0 hazard. Okay, so this is what the case is. And if you consider an example, consider a NAND SR latch with the following Boolean function of S and R. It is given. See here, you know this is your NAND latch, is it? And in which the input is connected here is AB plus CD, is it? And that is given as an input. Or you can, as you are using, this is a NAND latch, we must use the complement of SR, is it? Hence, we are making a complement and then we are connecting it to your S. Okay, that is why you will get it as AB bar dot CD bar. Similarly for is A bar C to the whole bar. So that is connected to your SR latch. Hence, if you consider here, see here, the Boolean function for output Q is, it is, a feedback is given here, is it? It is Q bar. And then yes, you know it is A B bar, is it? A dot B to the whole bar, is it? A dot B to the whole bar. And this is performing an AND operation, and this is also given to S, and C dot B whole bar is also given to S. These three operations are performing an AND operation, and then it is inverted, in which a Q output is NAND operation. That is why it is given here as Q bar, AB to the whole bar, and CD to the whole bar. And then for all these terms it is whole bar because it is a NAND operation at your Q. Is it? The output is generated with two levels. So this can also be generated with the two levels of NAND gates. Okay, see here, this NAND gate is eliminated, and hence we are giving directly to S, which eliminates the propagation delay, and hence your hazards can be reduced. Here the output Q is equal to 1, then automatically a Q bar is 0. If two of the three inputs goes momentarily to 1, if two of the three inputs, see, out of these three inputs, if any of the two goes to 1 for a momentary, the NAND gate associated with the output Q will remain at always 1 because your Q bar is maintained here as 0. That is why whatever be the changes in any of the inputs of A, B, C, D, that momentary change will not affect your output. Hence this will maintain, and the hazards can be reduced. Okay, that momentary change can be reduced when you try to use your SR latch. That is what the case that is discussed here.